There's a signal coming from 124 light years away, a chemical fingerprint floating in the atmosphere of a distant world, a molecule that, on planet Earth, has only one known source: life, marine organisms, biological activity. Scientists detected it not once, but twice, using two completely different instruments on the same alien planet. And here's what nobody is telling you clearly enough. The James Webb Space Telescope didn't just find an interesting chemical compound floating in space, it may have found the single most important thing in the entire history of human civilization. And the scientific community is quietly losing its mind. Something happened in April of 2025 that should have stopped the world. It should have dominated every news cycle, every conversation, every dinner table on the planet. Instead, it was buried beneath political headlines, stock market fluctuations, and celebrity gossip. A team of astronomers at the University of Cambridge published a paper. It was precise, measured, careful in its language, as scientific papers always are. But beneath that careful language was a trembling, barely contained revelation that humanity has been waiting thousands of years to confirm. The James Webb Space Telescope had detected, in the atmosphere of a planet 124 light years from Earth, a molecule called dimethyl sulfide. And on Earth, that molecule has exactly one known origin. It is produced exclusively by living organisms, specifically by marine microbes, by phytoplankton, by biological life. Think about what that means. Really stop and think about it. This was not a rumor. This was not a social media claim. This was peer-reviewed science, published in a major journal, produced by one of the most respected astronomical teams on the planet, using the most powerful space telescope ever built by human hands. And the signal wasn't faint or ambiguous. It reached 3 sigma statistical significance, meaning there is only a 0.3% probability that what they detected occurred by random chance. That is not a ghost, that is a pattern. That is something real, floating 124 light years away in the atmosphere of a world called K2-18b, whispering something that science has never been able to say before with this level of confidence. But here is where it gets more complex and far more interesting. Because K2-18b is not just any planet. It is not a scorched rock orbiting too close to its star. It is not a frozen wasteland drifting in the dark. K2-18b sits precisely within what astronomers call the habitable zone, sometimes called the Goldilocks zone, the narrow band around a star where temperatures are neither too hot nor too cold, where the conditions could theoretically allow liquid water to exist on a planetary surface. This planet has a radius 2.6 times that of Earth, and is about 8.6 times as massive. It orbits a cool red dwarf star in the constellation of Leo. And based on everything Webb has revealed about it, scientists believe it may be what they call a Hycean world, a planet covered not in rock and soil, but in a vast global ocean of liquid water, topped by a thick, hydrogen-rich atmosphere. An ocean world, a water world, sitting right where life could survive, and now apparently exhaling the chemical signature of biology into its own sky. The team, led by the University of Cambridge, detected signs of dimethyl sulfide and dimethyl disulfide in the atmosphere of K2-18b. These molecules are from the same chemical family and are considered potential biosignatures, chemicals that, when detected around a distant planet, could indicate the presence of biological processes. On Earth, as any marine biologist will tell you, these compounds rise from the ocean surface because microscopic marine life produces them constantly. Phytoplankton, algae, microorganisms that blanket our seas in invisible billions. They breathe, they metabolize, and as a byproduct of that living process, they release dimethyl sulfide into the air. It is one of the gases responsible for that characteristic smell of the ocean, that sharp, salt-edged scent that hits you when you stand at the shore. That smell, in a sense, is the smell of life itself. And James Webb smelled it from 124 light years away. What most people are not seeing is the extraordinary significance of what happened next, because the detection in April 2025 was not the first time the signal appeared. In 2023, and again in April 2025, a team using the James Webb Space Telescope detected molecules in K2-18b's atmosphere they claimed could be a biosignature. Dimethyl sulfide, a gas produced on Earth exclusively by marine life. The 2025 detection, however, was different in a crucial way. It used Webb's MIRI instrument, the mid-infrared instrument, which observes an entirely different wavelength range than the instruments used in 2023. This is an independent line of evidence using a different instrument than we did before and a different wavelength, range of light, where there is no overlap with the previous observations, the lead researcher stated. 2 separate instruments, 2 completely different wavelength ranges, the same signal, the same planet, the same chemical fingerprint. That is not coincidence, that is convergence. And this is where everything changes, because science does not move forward on single data points. It moves forward when independent observations, using different methods, arrive at the same conclusion. That is the gold standard. That is how you know something is real. And Webb, using two completely different eyes, looking at two completely different spectra of light, kept seeing the same thing in the atmosphere of K2-18b. The signal was reproducible, consistent, persistent. And the scientific team did not rush to proclaim the discovery of alien life. They were careful, measured, deeply skeptical of their own results, because that is what real science demands. The lead researcher stated, "It's important that we're deeply skeptical of our own results, because it's only by testing and testing again that we will be able to reach the point where we're confident in them. That's how science has to work." But read that statement again slowly. He's not saying the signal isn't there. He's not saying they were wrong. He's saying they need more testing, more observation, more data, before they can stand before the world and make the announcement that would fundamentally alter human history. The signal is real. The question is, what is producing it? Now, there's a counter-argument. There's always a counter-argument in science, and this one deserves to be heard. Some researchers have pointed out that dimethyl sulfide is known to be present in interstellar clouds and has been detected in comets, and that its detection in a planetary atmosphere, if real, could most likely be the result of abiotic, non-biological processes. In other words, chemistry might be doing something unexpected. Some unknown reaction chain, some exotic atmospheric condition that mimics what biology does on Earth could theoretically be producing this molecule without any living organism involved. And a separate NASA-led analysis, released in mid-2025, found no conclusive evidence of DMS and underscored the challenges of interpreting such signals while still confirming K2-18b's water-rich nature and revealing a complex atmosphere. This is not science failing. This is science working exactly as it should. Competing analyses, rigorous skepticism, multiple teams interrogating the same data from different angles. But notice something crucial. Even the analysis that expressed doubt still confirmed the water-rich atmosphere. It still confirmed the complexity of what is floating above that alien ocean. Nobody is saying K2-18b is barren. Nobody is saying the signal is pure noise. The debate is over-interpretation. And the interpretation that keeps being suggested, even cautiously, by one of the most prestigious astronomical research teams in the world, is that life might be the simplest explanation for what Webb is seeing. Here is the deeper context you need to understand why this matters so profoundly. For the entire history of modern astronomy, the search for life beyond Earth was always theoretical. We had equations, the Drake equation, the Fermi paradox, frameworks for calculating the probability of life existing elsewhere. We had the discovery of extremophils on Earth, organisms surviving in environments once considered completely hostile, hydrothermal vents on the ocean floor, acidic pools, the permafrost of Antarctica. These discoveries expanded our understanding of where biology can persist. We had the detection of organic molecules drifting through interstellar space, proof that the chemical building blocks of life are common across the cosmos. Webb itself, in November 2025, uncovered a trove of complex organic molecules frozen in ice around a young star in a neighboring galaxy, including a historically significant first-ever detection. Life's ingredients are everywhere. The universe is literally seeded with the raw materials of biology. But raw materials are not life. Chemistry is not biology. The gap between a molecule and a living organism is one of the deepest unsolved mysteries in all of science. And what Webb may have found at K2-18b is not just chemistry, it is a process. A metabolic process. The exhaled byproduct of organisms doing what living things do, consuming energy and releasing waste. Dimethyl sulfide is not a building block, it is an output. It is what happens after life has already assembled itself and started living. Think about that distinction, and think about what it means for our place in the universe. But the K2-18b discovery, as staggering as it is, represents only one of the ways in which the James Webb Space Telescope has been systematically dismantling what we thought we knew about the cosmos. Because while one team was quietly finding possible signs of life, the rest of the astronomical community was confronting something equally destabilizing. A crisis in our most fundamental model of how the universe itself works. This is not a story most science channels will tell you, not because it's being hidden, but because it requires sitting with discomfort. It requires admitting that a framework humanity has refined over a century of observation and mathematics might be deeply, structurally incomplete. That framework is called Lambda CDM. Lambda represents dark energy, the force accelerating the expansion of the universe. CDM stands for cold, dark matter, the invisible gravitational scaffolding believed to shape how galaxies form and cluster. Together, these form the standard model of cosmology, the accepted scientific picture of how the universe began, evolved, and became what it is today. And James Webb has been finding things that do not fit that picture. Webb's most disruptive finding remains the existence of massive, well-structured galaxies at distances corresponding to the first few hundred million years after the Big Bang. These observations have created a genuine crisis in early universe cosmology that ground-based telescopes never could have triggered. The data is too clean and too consistent across multiple observations to dismiss as calibration error or artifact. This is a machine operating at the L2 Lagrange point, 1.5 million kilometers from Earth, beyond the interference of our atmosphere, with a 6.5-meter gold-coated mirror collecting light that has been traveling across the universe for more than 13 billion years. When it says it sees something, and what it sees contradicts the textbooks. Within the first billion years after the Big Bang, Webb has revealed ultra-bright compact galaxies, blazing with intense star formation, far more luminous and massive than any theoretical model predicted could exist so early. According to the Standard Model, the early universe was supposed to be a place of chaos and simplicity. Small, irregular clumps of matter, slowly coalescing under gravity, building up into larger structures over billions of years. The first galaxies were supposed to be crude, unstructured, primitive. They were supposed to be the rough sketches from which the masterpieces would eventually be painted, but only much, much later in cosmic time. Instead, Webb pointed its instruments at the infant universe and found something shocking. Fully formed, massive, structured galaxies, not small and irregular, but enormous and organized, existing in a universe less than 500 million years old. Webb has identified candidate galaxies at redshifts above Zeus 10, light emitted within roughly 500 million years of the Big Bang, whose inferred stellar masses are higher than lambda CDM with standard star formation efficiency comfortably allows. These galaxies were already old when the universe was a baby. They had already assembled billions of stars. They had already developed structured disks, organized rotation, mature morphology, and according to the mathematics of the Standard Model, there simply was not enough time for that to happen. In 2025, Webb revealed a remarkable system of at least 5 interacting galaxies just 800 million years after the Big Bang, showing that galaxy mergers and interactions began far earlier than expected. This finding suggests that the cosmic web of dark matter filaments that guides galaxy formation was already well developed in the young universe. The cosmic web, that vast invisible skeleton of dark matter along which galaxies align and cluster, was supposed to take billions of years to fully assemble. Webb found it already functioning, already mature, barely 500 million years after the universe began. This is not a minor discrepancy. This is not a rounding error in the calculations. This is the equivalent of expecting to find a newborn in a hospital nursery and discovering a fully grown adult. And it gets stranger. Webb's view of the infant universe has delivered genuine surprises. Bright galaxies, rapid star formation, and evidence of accreting black holes only a few hundred million years after the Big Bang. These findings have ignited debates about whether our best cosmological theories can survive new data. Or supermassive black holes, objects that take billions of years to grow by consuming stars, gas, and everything unfortunate enough to fall within their gravitational reach, are appearing in Webb's data at the earliest epochs of cosmic time. They are already enormous, already feeding, already dominating the centers of early galaxies. The Standard Model has no comfortable explanation for their presence. Something grew too fast, too early, in a universe that should not have had enough time. Strange red dots in James Webb images, once a mystery that puzzled scientists for years, have now been identified as young black holes hidden inside dense clouds of gas, glowing as they devour their surroundings. But even this answer generates more questions. Because these black holes are not just unusual in their early existence. They appear to be a new category of object altogether, what some researchers are now calling black hole stars. Entities that blur the boundary between a massive star and a growing black hole, a hybrid of processes that our existing theoretical frameworks never anticipated. According to informed sources within the cosmological research community, what Webb is producing is not merely a collection of surprising observations. It is a systematic pattern of contradiction. Not one anomaly, not two, but a recurring sequence of findings across completely different types of objects, at different cosmic epochs, using different observational techniques, all pointing toward the same uncomfortable conclusion. The universe did not evolve the way our models said it should. Something fundamental about our understanding of cosmic history may be wrong, or more precisely, incomplete in ways that have consequences we cannot yet fully calculate. The Hubble tension remains, as of late 2025, the most significant puzzle in cosmology. The James Webb Space Telescope has verified local measurements of the universe's expansion rate, while early universe measurements from other instruments give a completely different number. The persistence of this disagreement suggests that the Standard Model of the universe may be incomplete. The Hubble tension, for those unfamiliar, is a crisis hiding in plain sight within the equations of physics. When astronomers measure how fast the universe is currently expanding, using stars, supernovas, and gravitational lenses in the nearby universe, they get one number. When they calculate what that expansion rate should be based on the physics of the early universe, using the cosmic microwave background, the faint afterglow of the Big Bang itself, they get a different number. These two measurements should agree. They don't. And Webb, with its extraordinary precision, has sharpened rather than resolved this discrepancy. The gap is real. The tension is not going away. And the only explanations that fit are either a systematic error, hiding somewhere in decades of careful measurement, or new physics, something operating in the universe that our existing equations do not account for. This is not a crisis of instruments. This is a crisis of understanding. Now consider what Webb has been finding on the planetary level, and the picture becomes even richer and stranger. Beyond the K218b biosignature story, Webb has been systematically analyzing the atmospheres of planets orbiting distant stars. With a precision that was science fiction just a decade ago, Webb's spectrographic capabilities have opened a new era in exoplanet science. Webb detected carbon dioxide, water vapor, sodium, potassium, and sulfur dioxide in a hot Jupiter's atmosphere. The first detection of sulfur dioxide, a photochemical product, on an exoplanet. That single detection represented a breakthrough. Webb was not just identifying gases, it was identifying the products of chemical reactions happening in real time in alien atmospheres, photochemistry, the same category of process that shapes the chemistry of Earth's own skies. The TRAPPIST-1 system, that extraordinary collection of 7 Earth-sized rocky planets orbiting a small, cool star just 39 light-years from Earth, has been another major focus. Several of these worlds sit within or near the habitable zone. For years, they have been considered the best nearby candidates for potentially habitable worlds. Webb's analysis found that TRAPPIST-1d does not have an Earth-like atmosphere, ruling out a category of habitability scenarios for that particular world. But this is not a failure. This is progress. Understanding which worlds do not have what we are looking for is as scientifically valuable as finding worlds that do. It narrows the search. It sharpens the question. And then there is Alpha Centauri, the nearest stellar system to our own. Just 4.37 light-years away, close enough, in cosmic terms, to almost feel like a neighbor. Webb has detected strong evidence for a giant planet orbiting Alpha Centauri A, the nearest sun-like star to Earth, located just 4 light-years away. A giant planet in our nearest stellar neighborhood. We did not know it was there, and now Webb has found it. The implications for the architecture of nearby planetary systems, and for the possibility of additional, smaller, potentially habitable worlds in that system, are significant. If a giant planet orbits Alpha Centauri A, the gravitational dynamics of that system become far more complex and interesting than we previously understood. What is the real story behind all of this? What is the thread that connects the biosignature of K218b, the impossible galaxies of the early universe, the Hubble tension, the strange black hole stars, the atmospheric profiles of dozens of alien worlds? The thread is this. James Webb is operating at the absolute frontier of what human civilization can see. It is not just looking at the universe, it is probing the limits of our understanding of the universe. And at those limits, the picture does not match the map. The territory is stranger than the cartography. The cosmos is behaving in ways that our best models, built over a century of brilliant science, did not fully anticipate. And this is not a reason for despair. This is the most exciting thing that can happen in science, because every time the universe fails to behave the way we expected, we are being handed a clue, a piece of evidence, a signal that the next version of our understanding will be richer, deeper, and more complete than what came before. Consider the organic molecules Webb has been finding. In a nearby galaxy, Webb uncovered an extraordinary concentration of small organic molecules deep inside the heavily concealed core, representing a remarkable find about the distribution of life's chemical ingredients across cosmic structures. Complex organic chemistry is not rare. It is not confined to Earth. It is not even confined to our galaxy. The building blocks of biology appear to be woven into the fabric of the universe itself, distributed across billions of light-years of cosmic structure, assembled by the same physics that creates stars and planets and the gravitational webs that bind them together. Life's ingredients are not an accident. They are a consequence of how matter behaves in the conditions the universe creates. The question is not whether those ingredients are available across the cosmos. They are. The question is whether, in enough places, they crossed the threshold from chemistry to biology, from molecules to metabolism, from matter to life. And what Webb found at K218b suggests the answer might be yes. The observations reached 3 sigma statistical significance, meaning there is only a 0.3% probability that they occurred by chance. The results represent the strongest evidence yet that life may exist on a planet outside our solar system. 3 sigma is not proof. In particle physics, the gold standard for claiming a discovery is 5 sigma, a 0.003% probability of a random occurrence. We are not there yet for K2-18b, but 3 sigma is not nothing. 3 sigma is a signal that demands investigation, that demands follow-up, that demands more telescope time and more careful analysis. And the researchers have stated clearly that they believe between 16 and 24 additional hours of Webb observation time could push the signal to a level of certainty that would be, by any scientific standard, definitive. Those hours of observation are being sought. The data is being gathered. Somewhere, right now, James Webb is pointing its golden mirror at a section of sky in the constellation of Leo, collecting infrared photons that left K2-18b more than a century ago, and feeding them into instruments sensitive enough to detect individual molecules floating in an alien atmosphere. The analysis is ongoing, the signal is being interrogated, and the scientific community is watching, because the next announcement in this story might be one that changes everything. But here is something that almost nobody is discussing publicly, even in the science communication space. The implications of a confirmed detection of life on K2-18b would extend far beyond biology. They would reach directly into the cosmological crisis that Webb has been uncovering. Because if life exists on K2-18b, a world quite different from Earth, in a system quite different from ours, at a distance of 124 light years, then the probability calculations underlying the entire field of astrobiology shift dramatically. The rare Earth hypothesis, the idea that life on Earth required such a specific and unlikely combination of conditions that it is probably unique in the universe, would face its most serious challenge. The Fermi paradox, the question of why, if life is common, we haven't yet detected evidence of civilizations, would sharpen into something even more urgent and mysterious. And if life exists on K2-18b, and life exists on Earth, and the universe produced both of them independently, then life is likely not rare. It is likely prevalent. In the universe we thought we understood, governed by physics that produces mostly dead mineral, the tension exposed by the James Webb Space Telescope, scientists argue, is a productive one, forcing us to rethink how complexity emerged in the early universe. And complexity is exactly the right word. Because what Webb keeps finding, at every scale and in every direction it looks, is complexity where simplicity was expected, massive structured galaxies where chaotic primitive clumps were predicted, biosignature molecules where barren chemistry was assumed, organic compounds distributed across galactic cores where sterile void was imagined, supermassive black holes already enormous when the universe was in its infancy. The cosmos keeps revealing itself to be more organized, more layered, more abundant with structure and chemistry and potential than our model said it should be. Something is operating in the universe that we do not fully understand, something that accelerates galaxy formation, distributes organic chemistry, enables the rapid growth of black holes, and creates the conditions for biology to arise in multiple places. We do not yet have the physics to describe it completely, but Webb is giving us the data to start building that physics. Every impossible galaxy is a constraint. Every biosignature is a data point. Every atmospheric spectrum is a paragraph in a story we are only beginning to read. What happens next? The follow-up observations of K2-18b are the most immediate answer. If the biosignature signal strengthens, if it crosses from 3 sigma to 5 sigma, science will have to confront the announcement it has both dreaded and longed for. Not in the sense that finding life is dangerous, but in the sense that it fundamentally transforms every question humanity has ever asked about itself. Who are we? Are we alone? What is consciousness, and how common is it in a universe that apparently builds biological processes? Into ocean worlds around red dwarf stars. Is the universe itself, in some sense, oriented toward life? Not in a mystical sense, but in the physical sense that its laws and constants and the chemistry they produce make biology an inevitable outcome in enough places? Meanwhile, the cosmological crisis will deepen. A smaller group of researchers argues that Webb's findings challenge the standard cosmic timeline itself, potentially requiring adjustments to the cosmological constant or dark energy models. None of these explanations is universally accepted yet. More data will arrive. More early galaxies will be confirmed. More tension with the standard model will accumulate. And at some point, perhaps in the next 5 years, perhaps in the next decade, a new framework will emerge. A new understanding of how the universe builds structure, how dark energy and dark matter interact, what the true age and expansion history of the cosmos actually is. That framework does not exist yet, but the evidence Webb is gathering will make it inevitable. There is something profound happening right now in 2026 that deserves far more attention than it receives. Humanity has built a machine that can see across 13 billion years of time, that can detect individual molecules in the atmosphere of a planet orbiting a different star, that can photograph galaxies that existed when the universe was less than 500 million years old. And that machine is systematically revealing that the universe is stranger, richer, and more alive than we assumed. The map was too simple for the territory it was trying to describe. And now we are redrawing the map. The questions being raised by every Webb observation do not have clean answers yet. Did life arise independently on K2, 18b? Are there other Hycean worlds, covered in alien oceans, exhaling the chemical byproducts of their own biospheres into atmospheres that drift across 124 light-years of space before arriving in our instruments? What are those impossible early galaxies telling us about the physics of the infant cosmos? What is producing the Hubble tension, and what new category of physics will be required to resolve it? What are those little red dots, those black hole stars? And what do they mean for our understanding of how mass and energy behave at the earliest moments of cosmic time? Nobody has all the answers. Not yet. But James Webb is asking exactly the right questions. And every answer it finds opens 3 more doors, each leading into a corridor we did not know existed. The universe is not the quiet, mostly empty, mostly dead expanse we once imagined. It is something far more extraordinary, complex, layered, chemically rich, structurally surprising, and quite possibly alive in ways and in places we are only beginning to comprehend. The signal from K2 18b is still there, floating in the data, waiting for confirmation, waiting for the follow-up observations that will either strengthen it into something undeniable or reveal it to be something abiotic and unexpected. And the impossible galaxies are still there too, in the infrared images Webb sends back to Earth, massive and structured and organized, sitting at the edge of cosmic time, defying the models that were supposed to describe them. Something out there is waiting to be understood, something that will change the way every human being on this planet thinks about where they live, who they are, and what kind of universe they were born into. The telescope is still watching. The data is still coming. And the most important discovery in human history might be sitting right now in an astronomer's data set, waiting for the analysis that will finally make it undeniable. What happens when that moment arrives, and what we are prepared to do with it? That is the question nobody is ready to answer.